In this video, we're going to discuss the very basic chemical reaction. Chemical reactions denote change, and chemical reactions come in various types. Now, the information presented in the chemical reaction, all reactants before the change are on the left. On the right side of the arrow, all the products after the chemical change. Now, it doesn't matter which order you write the individual reactants or the individual products within a reaction equation, as long as all the products are on the right and all the reactants remain on the left. After each component of the reaction equation, we denote the state of matter under the current reaction conditions by an italicized letter in parentheses. In this example, the state of matter of each one of the components is gas. But we can also have S for solid, L for liquid, as well as G for gas, and AQ for aqueous, meaning dissolved in water. The most important information in a chemical reaction equation is the stoichiometric coefficients. These are the numbers preceding each one of the individual components of the reaction equation. These denote the mole ratios in which the reactants react and the products are produced. In this example, the stoichiometric ratios tell us that for every 4 moles of ammonia we react, we need 3 moles of oxygen, and we're going to produce 2 moles of nitrogen and 6 moles of water. However, we're not always going to be reacting these exact quantities. For example, if we want to react 4 moles of ammonia, we need to know how many moles of oxygen are required, how many moles of nitrogen and water are produced. In this example, this is very obvious because we've simply doubled the amount of ammonia, which means we're going to double the amount of oxygen, nitrogen, and water. But we're going to use dimensional analysis and the stoichiometric ratios to be absolutely sure, because it's not always going to be this simple. Whenever performing stoichiometric calculations, you always start with the information or the values you have been given. In this case, 8 moles of ammonia. We are going to use the stoichiometric coefficients as the ratios in which these react and produced. So if we want to find out how many moles of oxygen are required, we're going to use the 3 moles of oxygen to 4 moles of ammonia ratio in which they react. We're going to use dimensional analysis to make sure that our units cancel properly, in this case leaving us with nothing but moles of oxygen, multiply the values, and as expected we get 6 moles of oxygen required to react with 8 moles of ammonia. And we do the exact same thing for nitrogen and water. We start with 8 moles of ammonia, multiply that times the 2 to 4 mole ratio of nitrogen to ammonia, and we get, as expected, 4 moles of nitrogen produced. And we can prove this with our dimensional analysis. The units cancel out, leaving us moles of nitrogen. And finally, with 8 moles of ammonia, multiplying that times the 6 to 4 ratio of water produced for moles of ammonia reacted, we get, as expected again, 12 moles of water produced. Dimensional analysis checks out. However, like I said, this is not always going to be the case. So for instance, if we are reacting 1.75 moles of oxygen, what's the minimum number of moles of ammonia required? How many moles of nitrogen are produced? And how many moles of water are produced? In this case, it's not as obvious as it was before because it's not a whole number ratio of our original stoichiometric coefficients. So again, we start with the values we're given. So starting with 1.75 moles of oxygen, we're going to multiply that times the 4 moles of ammonia per 3 moles of oxygen ratios, stoichiometric ratios. Check our dimensional analysis. Moles of oxygen cancels, leaving us with just moles of ammonia. And we get a value of 2.33 moles of ammonia. Same thing for nitrogen and water. 1.75 moles of oxygen, multiply that times the stoichiometric ratios directly from the reaction equation. We get 1.17 moles of nitrogen. 1.75 moles of oxygen multiplied times the 6 to 3 ratio of water to oxygen gives us 3.5 moles of water. And again, the dimensional analysis checks out. So this is the basic information presented in a chemical reaction equation and some very basic examples of some calculations using the stoichiometric ratios.